Sweet. So I will say this to start. Let me share my screen.
Okay.
And there is sort of a workflow to designing PCBs, and KiCad has all these different features. I'm just going to open KiCad 9.
Okay.
Okay. So inside KiCad, you have all these tools, and I'll say that the probably the top four are the most important ones that you're going to use.
Okay.
Okay, so the top four here, like being the schematic editor, the symbol editor, the PCB editor, and the footprint editor. Um,
Okay.
and really, they're like two pairs of two things. The schematic editor is just where you outline the circuit that you're trying to actually implement. Like,
Okay.
uh, by definition, the schematic is like the electrical diagram of your circuit. So it's going to contain like your standard capacitor symbols, your standard resistor symbols. So like, for example, I'll just open the schematic for this PCB that I was working on
Okay.
because there's a ton of files here, but a lot of them are manufactured. So this is what I mean when I say the schematic. The schematic is just all of the symbols of all the components. So I've got resistors, I've got capacitors, I've got inductors here, right? I've got connectors because you have to have a symbol for every single part that you want to put on your PCB.
Okay.
Okay, so each of these things is called the symbol. This would be considered the symbol for the resistor. It's just the squiggly line. And,
Okay. So
and
it's like everything we saw in circuits one.
yeah, yeah, exactly. And so there's some other stuff in here that you probably haven't seen yet. Like I don't know if you've taken electronics yet, probably not, but this is like a
No.
transistor. You've probably heard of
Okay.
transistors.
Yeah, I have.
So this is a transistor. This is like a BJT. And let's see if there's anything else fancy in here. So this is like a big chip, in the end of module 5, I was talking about like chips and how they have different packages. You've got
Mm-hmm.
these like this black box with all the legs on it. So that's what this is. This is a chip. And usually the manufacturer will actually provide you with the symbol. So you don't have to like create that on your own, but you can also create
Nice.
symbols on your own. I'm just showing you this schematic just so that you know what it is. When I actually go through like my tutorial part of this, I'll probably just make a schematic from scratch so you can see the process. Um,
Perfect.
but just to know this is what the schematic looks like. And like I said, these are all the symbols. So if I close this, you see that there's the two things that are grouped together at the top are the schematic editor and the symbol editor. So
Mm-hmm.
the schematic editor is where you build the schematic, and the symbol editor is where you can edit or add new symbols. So like the basics are already in KiCad. You don't have to make those, like resistors and capacitors and transistors, all the things that you would normally find. Those symbols are already built into KiCad. So if I click on symbol editor, you'll see that it's opening up this whole library of symbols that are already built into KiCad.
Mm-hmm.
So if I just type resistor, and I click here, this is like I guess this is a European software or something. So this is actually the symbol they use for resistors in Europe. But if you click here, it's the US symbol, and
Mm-hmm.
that's like the standard one that we've seen. Okay.
Okay.
So there's all these different devices. You can type anything you want here. You can type capacitor. If I type C, there will be a capacitor, and you see all these symbols. So these are all built into KiCad. You don't have to make these.
Mm-hmm.
So, and I personally, when I'm trying to design the board, I don't want to have to make anything custom, but inevitably, the more complicated your system, you eventually have to do some custom stuff
Right.
because, but like most of the stuff, like if you're doing all passive components, for example, like capacitors, resistors, and inductors, all of those symbols will be here, but it's when you start to invoke, like if I wanted a 555 timer, for example. Have you heard of that chip before?
Yeah.
So
Yeah.
if you wanted that, they may or may not have it in KiCad. You might have to go find the symbol yourself. So I'll type 555. Oh, they actually do. Look at that. So they have a symbol for the 555 timer built in also. And that's another really nice thing about KiCad and like Altium as software is that there is a ton of stuff already built into the software. But
That's very useful.
you have the option to create your own symbols. So like if there was some obscure chip that you were trying to use, let me just show you. If there was some like weird chip that you wanted to use, you might go File, New Symbol, for example. Actually, I think you need to hold on. Sometimes you have to create a new library before you can actually create a new symbol.
Oh,
Okay, let me close this. Symbol library timer is not writable. Okay, maybe I have to click on. So I already have a custom library in here called Skelly Custom. I might have to right click. Yeah, okay. So you do have to create a library first. So if you say new library, that's where you're
hmm
gonna put your custom parts. So like you can say you could just say custom underscore parts. For some reason my thing is defaulting to this weird KiCad folder, so I'm gonna go to documents. KiCad 9 and then symbols. So I'll call it, I'm just gonna say put your initials here
okay.
just as an example. Okay, so I just created this library called custom parts, and now like all these other libraries have symbols in them already. These are built-in
hmm
symbols, but yours has nothing in it technically because you haven't put anything in it yet. If I right click and I say new symbol, now it's going to ask you for some things that you might want to build. So let's just say we were trying to build our own custom inductor, or let's just do a resistor, uh, for just to be simple.
Okay.
You would name it resistor custom or something, and then you just say I don't know what some of these settings are. It probably doesn't matter, but you just want to get to the point where you have this blank screen. And then
hmm
you could start drawing here. Like you could just take this line tool and you can, start drawing and you could make zigzags and do all the stuff that you want to do to make your custom symbol. So
Okay.
so basically like I aim at using things that are already built in because it just saves time. But if you needed a custom symbol, you can make one. Okay? That makes sense.
Awesome.
Okay,
Yeah.
so that just as an overview, that's the sim and these are the symbols that go into the schematic. So we haven't done anything with the PCB yet. This is all just the schematic, which is like a
hmm
representation of our circuit, but that's the first step before you can even go to the PCB is you need a schematic.
Okay.
Because what you end up doing is here, let me just close this. I'm not going to save this. Okay, so the symbols and the PC and the schematic are linked. Symbols go into the schematics. That's important.
Okay.
Okay. And then the
hmm
PCB and the footprints are also linked because what the footprint is it's telling us what is the actual, sometimes it's called a land pattern. I think I showed this in module 5 actually. The footprint is where the part that you're going to physically put on the board, where is it going to sit? Like, where are you going to solder it? Because it needs to be soldered onto the board, right?
Yeah.
So the footprints look a little bit different because what they are is they're actually like a three-dimensional thing. Schematics are all 2D, right? It's just a drawing. But
hmm
footprints are actually like a real three-dimensional thing that's going to go on the board. So the software is mainly in two dimensions, like you're looking down on the PCB. That's kind of how it is. It's everything's planar. But
Right.
it's important to keep in mind that PCBs are like a three-dimensional thing because there are different types of footprints. Some that I think again I mentioned this in the module, but like some of them are surface mount, which means that they sit on the surface of the board, and then some
hmm
of them are through hole, which means they go through the PCB. Okay,
Okay.
so again, if we open up this footprint editor, we have all these built-in footprints. Okay, and now, if I go and look over here at capacitors, they have both SMD, which means surface mount types of capacitors, and they also have through-hole types of capacitors. So they have both
Okay.
types. And so if I just wanted to go look at one of these capacitors, you'll click on it and you'll see that there are two holes, like physical holes, that is where the part would actually, like the legs of the part would actually go through those holes on your circuit board. Okay.
Okay.
And if you had a surface mount part, it would be different. It would have two pads. There's no hole in the pads. They're just pads that are going to sit on top of the circuit board.
Okay.
What's really nice about KiCad and it's not common to other softwares, but like Altium is similar, is that you can actually view the 3D viewer at any time while you're working with the PCB, and it will show you what this thing looks like in 3 dimensions, which is awesome.
That's really cool.
So this is the 3D viewer of that capacitor. Not only is the footprint there, but the actual 3D model of the capacitor is also built into KiCad, which is super nice. I love having 3D models in my circuit boards because it gives you a feel for how much space they're going to take up, especially when you're trying to make things compact. You can see how how tightly can I actually pack these components realistically if you have
Yeah.
a realistic 3D model, and then you can get a really good feel for like, are these things actually going to fit together? Are they going to collide? Because if you notice, like, look at this white line here.
Mm-hmm.
If I go back to the footprint, that's this yellow part right here. In
Oh,
in theory, you could put like another component here, like you could put a pad here. But when you look at the 3D viewer, you notice that the actual capacitor took up all of this space. So it's helpful to have the 3D model so that you know, oh, okay, I actually can't put anything in that space.
okay.
And I'll go back to the through hole one just so you can see that also in 3D if you go 3D viewer. So this is one that has legs that physically go through the board.
Nice.
You can see that, right? So this is the difference between a through hole part and a surface mount part is that with through hole, you have these you can actually see inside the board, which is kind of nice. There's literally like a copper cylinder that will connect the top layer pad down to the
Mm-hmm.
bottom of the board. And through hole parts are good for a lot of reasons. For one, they are obviously like more mechanically stable on the board if you care about that. But then also there are just some parts that come in through hole versions that are like rated for higher voltage or they might be rated for higher power. So you might only be able to find that part that you're interested in through hole, and then you would need to use a through hole footprint. Okay.
Makes sense.
So hopefully it's clear that the footprint itself is just the thing that the part sits on. So if I were to
Mm-hmm.
take this 3D, I think you can actually hide it if you want. Let's see. Through hole models. Okay, so this is the footprint. This thing right here that includes the pads and it includes this white stuff which is called silk screen. You can write that down if you want. It's called silk screen, unless you already knew that. But that is the stuff that is used all over the PCB to label things. It's called silkscreen. And so usually you'll use it to put little designators so you know like what part this is. You'll use it to indicate polarity. So like for this capacitor, they put a little plus sign. I don't know why it's not letting me show the model anymore. Oh, there we go. They put a little plus sign here to indicate that this leg is connected to the plus side of the capacitor and this leg is connected to the minus side.
Mm-hmm.
So you can use the silk screen to do all kinds of things, but the main point that I wanted to make is just that this thing itself is the footprint. And so when we go back, I'm going to close this now. When we go back to the schematic, which is the place where we start, every single symbol has an associated footprint. So if I click on this resistor, you'll see down here it says footprint, and it's this particular footprint. And that
Okay.
that has to be the case because what the symbol is just telling us like you, the designer, you know what this circuit looks like. Theoretically, you've already designed this. And let me just make this point clear too. KiCad schematic viewer has absolutely no like simulation capabilities. It's not like LT Spice where you can like run this. It's literally just a visual thing for you, the designer, to use. So if you're designing a circuit, you'll probably want to run simulations somewhere else. And then you'll come into KiCad when you're already like confident in your circuit design and you put the circuit into KiCad because KiCad is not checking voltages or currents or anything. It's literally just a place for you to draw the schematic for your own reference.
Okay.
Okay. And so then when you do draw the schematic, which is the first thing that you do, you physically go in. So like, let me put a new part. I'm just going to place symbols. You can see that I can like pick a symbol. I'll just pick a resistor, very basic. And when I place this resistor, because this is just a symbol, you'll notice that at the bottom of the screen it says footprint unknown because there is no footprint until I assign a footprint. Okay.
Okay.
The reason being that resistor is a very general component, right? But
Mm-hmm.
there's all different types of resistors out there. So instead of you having to make a different symbol for every resistor that you want to use, you can just use the same symbol over and over again and assign different footprints.
Okay.
So like if I wanted, I could, here, let me just make a copy of this. And so here's like two resistors.
Mm-hmm.
I can go and if I hit E on my keyboard, that brings up the properties of the resistor. Or I think you can also right click and go to properties. Let's see. Yeah, properties. But you see how it says E. So you could just click E on your keyboard and that also works.
Okay.
So if you click on it and then you say E, it will bring up the properties and you can actually go and add a footprint to that symbol. Okay. So
Okay.
my resistor, let's just say I click on footprint and I'm going to click on this little library. That will allow me, okay, that will allow me to come into this footprint selector. So this is pulling from the whole library of the footprints that we have. And I might just type resistor. And now you'll see there's all, and it'll show you a little picture of what these symbols look like. So you can start clicking through and like you could pick the type of resistor footprint that you wanted. And these are
Okay.
all very standard types. So like if you, have you ever used DigiKey?
No.
Okay, so let me quickly introduce you to DigiKey. This is all just introduction, by the way. I just want to like show you everything before we do the actual design,
Yeah.
just so that you're familiar with the stuff. So DigiKey is like the go-to parts manufacturer. Okay. So they distribute all the electrical components that you could ever want. Switches, motors, resistors, capacitors, inductors, anything that you can think of, it's probably on DigiKey. And if it's not on DigiKey, the other one is called Mouser. So just maybe write those two things down. Those are really, really useful. This is where you find every part that you're ever going to be looking for.
Okay.
Or Amazon. Like you can always go on Amazon and get like LEDs and like basic stuff. But if you're looking for, true electrical grade parts, you probably want to go to DigiKey or Mouser. Okay, so I'm going to type resistor and I'm going to just hit enter. And it's going to give me all these options for the different types of resistors they have. They have through hole, which you've probably seen these before, of course.
Yeah.
Then they have these are called surface mount or chip resistors. And then they have all these other various things that you could click on. But really, these are the two main ones. And you see they've got like millions of options. So let's just say I'm going to go do a surface mount resistor. They
Mhm.
give you this whole entire table of things that you can choose from to start limiting what you're looking for. So maybe you start by saying, well, I know for sure I want like a 1 kilo ohm resistor. So you can
Okay.
go and you can find the resistance thing and you can type kilo ohms, one, oh, 1 kilo ohm, and then you can say apply. And it will now limit the search and it just eliminated like 800,000 options.
Wow.
Okay, so now you have all these 1 kilo ohm resistors. Well, I did max 1 kilo ohm. You probably would want to do min and max 1 kilo ohm so that you just don't get any other options. So now there's only 4,000 options. Okay, so that's good. And you can even further limit the options if you want to pick in stock, which is a good thing to pick because now, okay, 3,000 more options just went away. And then maybe you want to make sure that this thing can handle at least 300 milliwatts. Now we only have 11 options. Okay, so you say apply, and now it just gives you the options for the resistors that they have available that meet your specs. So it's like this is how people buy parts. And it's a very, very, very efficient way to buy parts because they give you all these filters that you can just throw out all the options that don't meet your specs.
Hmm.
Okay. So the reason I wanted to show you this was because I wanted to show you that if I click on one of these resistors, it will tell you that the package is a 1206 package. Okay. If
Okay.
if I go back to KiCad now, you notice that there's all these like sizes for resistors.
Yes.
1206 is one of the sizes. So if you were to buy that resistor, then you would need this footprint.
Okay.
Does that make sense?
That does make sense. You kind of have to like plan ahead, I guess, while you're doing it.
Yeah, so you might so it's kind of like yeah, multiple things are happening at once. typically you will build the schematic first and you'll test to make sure that the circuit is actually going to work. And that's purely schematic and simulation based. That's not even considering real parts yet. Then you
Mhm.
say, okay, I've built the circuit. I'm happy with it. I'm going to check my simulation to see how much power does this particular resistor need to be able to withstand. Let's say it needs to be able to withstand 100 milliwatts. That means that you need to buy a resistor that can handle at least that much power, or when you put it on your board, it's going to burn, right? So then that's the stage where you start saying, okay, what are the specs I need to make sure that these parts meet? And then you start going and picking parts while you're picking footprints because ultimately you're going to have the schematic in here with all these symbols, but there won't be any footprints yet. And then the footprint is heavily determined by what part you actually need physically. Okay.
Makes sense.
Okay. So yeah, and so just to show you like all these different sizes, 0402, 0603, these are just getting increasingly larger in size. The smallest possible one is 0201. This is like a ridiculously tiny resistor. It's like the size of a period on a page. Like it's really small.
God.
But like 1206 is like a reasonably sized, like maybe half centimeter thing. And as you go up, you'll see larger and larger and larger ones. And so that's how you pick the footprint for the. All I was trying to get at here is that every single part you get to personally decide what the footprint is, even if the
Mhm.
symbol is the exact same.
Okay.
Does that make sense?
Yeah, makes sense.
Okay. So then once you have allocated footprints to all of your parts, you do this thing where you can open the PCB editor, and that's here. Mine's already done, so this is like an example. So you'll see my board, but this is just an example.
Okay.
When you first open the board, like this isn't what it would look like. You would have all of these footprints, like this one, for example. I'm just gonna take it out and just throw it over here. You'll just have all these footprints just floating around in space with these little blue lines on them. Okay, and these blue lines are called rat lines. And what they are is they're little indicators of where things are supposed to be connected. Okay. So if I go and grab this other part here, I'm just going to grab this other part to show you. This is a capacitor. And you can see that KiCad is telling me that there's a rat line from this middle pin of this part over to this pin of this part, which means that that is a connection inside my schematic, and I actually
Mhm.
need to make that physical connection on my PCB.
Okay.
Okay, so right now this part is sitting here, this part is sitting here, and they're not connected. And if I want to connect them, I do this little router here. It says route single track or route tracks, and
Uh-huh.
it will click and you just drag, and now you've made a connection. And now this is a physical copper connection from this pad to this pad on your circuit board. And you'll notice that the blue line disappeared because
Yeah.
now I have made a connection.
Oh, okay.
Okay, so really the goal of the PCB design is you build the schematic,
Mhm.
then you assign footprints to all the parts.
Okay.
You open the PCB editor and you pull all of those parts in, but they're just going to kind of be all over the place, like I said, not connected, kind of like this. And then
Yeah.
once you have connected all of the blue lines, you're done. That's what you have to do. And then you order the board. So
Okay.
there are periodic checks that you can take to make sure that you haven't like missed anything or misconnected anything. But
Hmm.
KiCad makes it really hard for you to misconnect things. So if I'm gonna like, you know that this pad needs to be connected here. They actually have the same name, RF in. That's just like a node. I talked to
Okay.
you guys about how all the nodes in your circuit are gonna have the same potential. So
Hmm.
if you were to try and connect here to here, KiCad's happy with that. If you try to connect this to the other pad, it won't even let you because KiCad is
Okay.
like, no, that's supposed to be connected here.
Hmm.
So it knows based on your schematic that this is the connection that you're supposed to make. So it's very important to make sure your schematic is correct because if your schematic is incorrect, then your PCB will be incorrect. Does that make sense?
Yes.
Okay. So that being said, I'm going to undo what I've done so far with this just because I don't want to ruin my PCB. And then I'll close this. And okay, let's go and start a new project. I think I've basically covered these four things. Do you have any questions about anything I've said so far? I know I'm gonna say a ton of stuff and you'll probably have questions, so please stop me at any time.
It's all making sense for now. It's just now I just need to indulge myself in it, you know?
Yeah, no, for sure. You definitely like I would definitely advise you to go back. And also I'm recording this, so I'll send you the link when it's done so you can like go back and
Perfect.
rewatch. Um,
Yeah.
but I would definitely like encourage you to just go back afterwards and do it all yourself if you want to just follow the same steps and then you could even order the board if you want. But like what I'm gonna do in the example probably won't be cool enough to be worth ordering. So you might
Yeah.
want to do something that's like a little bit more fun.
Okay.
But I'll do file, new project, and I'm just gonna put it in my KiCad 9 projects, and I'm just gonna call it uh is it Natalie?
Natalie.
Is it it's pronounced Natalie? Okay, awesome.
Yeah, it's just Natalie.
Okay, cool. I'm not sure. My wife is Mexican, so I'm learning how to
Oh,
pronounce things in Spanish.
oh, that's sick.
Yeah, I'm trying to learn Spanish, but it's an uphill battle.
Oh, you got it. To learn Spanish, I think the best way is to just live in Mexico for a little bit.
No,
You
that's
just,
literally what everyone's told me. I need to figure out how to make it happen.
yeah.
Maybe
Yeah.
one day if I go on like sabbatical or something for some time, we could just go and spend some time in Mexico. Because we went to Costa Rica for our honeymoon and
Oh.
we were only there for a week and I felt like I was getting pretty comfortable like just speaking to the native people in Spanish from only a
Hmm.
week. So I'm sure if we were there for like 6 months or something, I would be totally fine.
Oh, you would have been fluent.
Yeah, that's my hope because we're having a baby actually very soon. Um,
Oh, congratulations.
thank you. Yeah, our first and it's a baby girl and we're super excited.
Oh.
And my wife is gonna teach her Spanish. And so I'm hoping that as she's teaching her, I can also like try to learn.
Yeah,
It'll be good.
that'll be good. Raise a bilingual child.
Yeah. Yeah, my wife is super determined. She's like, I will not let her not learn Spanish.
Yeah,
So
I
we're
have
gonna
a
make
lot of friends who are also Mexican and their parents didn't teach them Spanish and they're super sad. They're like, man, I missed out.
Are you bilingual also?
I am, yeah.
Okay, yeah. See, it's so cool. Like my wife also just gets like a bunch of cool work opportunities because she's bilingual, so she can do
Hmm.
like way more stuff, which is awesome.
Yeah, it's really
Um,
cool.
okay, so I just wanted to point you to this. I made a new project and notice how right off the bat it gives me a schematic and a PCB file
Okay.
because that's really what you need to build the thing. You need a schematic and you need a PCB.
Okay.
You start with the schematic, of course, but let me just show you so you know. If you click on the schematic, it's blank,
Hmm.
of course, because we haven't done anything with it yet. And if you click on the PCB, it will also be blank. It'll just have nothing in it. Okay.
Okay.
So to start, everything is blank, and let's just go into the schematic. So let's say we just want to make like a very simple circuit. I'm gonna do like maybe a circuit with an input, like a connector, and
Hmm.
then some resistors and some LEDs or something. Just something very basic. So let's just start with the resistors. So if I go place symbol, I like the US symbol just because it's the standard one that I look at. So that's the one that I would use. But if you just type R, it will give you all the options for the different types of resistors that you can see. So I'll take RUS and I'm just gonna put it down in my circuit. I'll put one here, and then you can go back here and get another one, or you can click and you can do Control C, Control V, like
Okay.
copy and paste, which is really nice. And so I've got these two resistors, and then I will go and get some LEDs. If you go and type LED, they'll give you an LED symbol, which is really nice. They also have like RGB LEDs and all these other packages that you can find that are super fancy. I'm just going to do basic ones. Let's just do the standard LEDs, two
Okay.
pins. So I'll say OK. And then you can hit R on your keyboard to rotate them. So I'll put these two LEDs in series with my resistors, copy paste. I think there's also a symbol called LED filled, so you don't have this weird like line going through the symbol. They
Oh,
have symbols for like everything, so I'm pretty sure they have a filled one. Let's see. Yeah. So this one is like a filled version, which, if you care about that, then I care personally. I think it looks bad with the line through it, but I'll leave it for now. So it's really up to you.
okay.
Okay, so you got your symbols, and just like any other schematic, you want to connect them with wire. And
Hmm.
there is a W shortcut on the keyboard that you can use to pull up the wire. Or you can click, I think over here somewhere it's got, yeah, draw wires. So you can do
Okay.
that. If
Yeah,
you
I
if you
definitely prefer the keyboard shortcuts.
Okay, great. Yeah, I also do. It's just way quicker. So I
Yeah.
usually keep like one hand on the mouse and one hand on the keyboard, and I'm just like trying to. Same with LT Spice.
Hmm.
I use all the keyboard shortcuts.
Yeah,
So
super helpful.
so one thing to know is if you are gonna click the W, as soon as you click it, it starts drawing. So
Okay.
as soon as I'm gonna click it, it starts drawing. And then if I hit escape, I still have the wire tool. You can see the little like a horizontal line there. If I hit escape
Hmm.
again, then it gets rid of the wire tool. But when I first click it, it starts drawing. So I can either start immediately wherever I want. So like if I wanted to start here. Oh, actually, if you hover your mouse over it, it brings that tool up. You can see it pop up on there.
Oh yeah.
You can just do that too.
So
So
you don't miss it.
yeah, so you can do that and just draw. And then if you want to end the connection, you just click and you double click and it will just close off the connection. I think if you're clicking out into open space, it will double click. And if you just want to connect it to another wire, you just have to click once.
Okay.
So from here to here, I'll connect. From here to here, I'll connect. And then I'll connect. I'll make another little bottom node here. It's a really good habit to get into the practice of doing also. Or sorry, a very good practice to get into the habit of doing to label all of your nodes. So there's this little net label. They also call them nets. I think I used this like interchangeably in circuits one.
Hmm.
If you click place net labels, you can label. So I'll just call the top one, let's just call it V1, for example. And then
Okay.
you can just place that on that net. And so now this entire net is going to be called V1. So everything connected to it will be called V1.
Okay.
And then maybe I want to name it's not super important because if you don't name them, then KiCad will auto name them, which is very
Mhm.
similar to like what LT Spice does. Like it'll just assign some net name. So
Yeah.
if you care about the net and it's like an important net, I think it's good to name it. And if you don't, then KiCad will just name it for you.
Okay.
So we can call that one V1. Maybe we even call it V plus because it's going to be the top part. And then we can call the bottom part V minus. So another net label. Okay, so I've got my V plus and my V minus, and then these, you could name these nodes too. They're obviously separate. You can see
Mhm.
right now it has its own name. It says net D1 slash A, and if you click on this one, it'll say net D2 slash A. So that's like the default name. But if we click down here, then it says V minus, and if we click up here, then it says V plus. Okay. So it gives you the option to name them or it'll auto name them. And so now we've got our resistors and our LEDs. What we probably need is some sort of power source. And so
Mhm.
you have a couple options. Like if you wanted to, you could put a battery pack on the board and you could like pop like a AA battery in there or something. Alternatively, you could put a little connector so that you can just put like a red and black wire in from a power supply. So it's really up to you. I'll just use a connector because it's just simpler.
Okay.
But if you wanted to, you can come in here and type like battery, and then it'll give you a little battery symbol. So,
Okay.
uh, do you have a preference or
No
not?
preference.
Okay, so I'll just use a header. If you do con, it's like connectors is the type, so it'll bring up this whole library of connectors, and I'll just use like a two pin. Let's see if I can find a good like header. Um, They have some nice ones sometimes. Let me see if I can type header and see if that happens. I guess not. This is just a place where I'm going to connect two wires, so it really doesn't matter. I just need some kind of a symbol. So
Okay.
this is fine. I'm going to mirror this. Okay. So this is where I'm going to connect my V plus and my V minus
Okay.
when I build the board, if I were to build this, because you have to like connect power in somehow.
Makes sense.
Okay. So this could potentially be my completed schematic. One thing that you probably want is a ground symbol.
Mm-hmm.
So you can click on this little power symbols button here, or you can hit P on your keyboard,
Mm-hmm.
and it will bring up all the different types of power symbols that you might want. And ground is one of those types of symbols. So if you go scrolling or type G and D, you can get a little ground symbol, and then you can just attach it here. I guess I didn't realize that that is now coinciding with my V minus, so I'll just get rid of this V minus and it'll just be ground. And
Perfect.
so this net is called ground. Okay.
Mhm.
So this would be in theory my completed schematic, but let's say that we actually care to add some details, like we want to know what color LEDs these are and we want to know what value resistors these are, for example. You can go in and you can change those things. So let's just say that we want to use like I don't know, 200 ohm resistors. So you can actually change the value to 200 and you can say okay, and then you can change this one also just for your own like reference.
Mhm.
And then if you wanted to, we don't need to do this, but you can go in there and you can actually link the data sheet. Like you could sit here and like put a link to the data sheet. So if you were on, for example, KiCad and you went and found a 200 ohm resistor that you liked that you knew met your specs, you could link it there. And then it also gives you the option to just add a description. So if you wanted to, you could say something like 200 ohm resistor from Ohmcraft, I don't know, 1 watt. Like that could be your description, and you can choose to show or hide that on the schematics. If I choose show, then that whole descriptor will actually pop up. But you can also just choose to hide it and just keep it here for your own reference.
Okay.
Okay, so
That's
you,
cool.
yeah, you have that. It gives you a lot of options just for the sake of like staying organized.
Mm-hmm.
Okay. And then, of course, let's just add details to the diodes too. Let's say we want to make this one a green LED. So let's just say description green, and I'll show that. And then I can move that. You can hit rotate and just put it wherever you want. And then let's make this one a red LED. So we'll just say description is red, and we'll show, and then we'll go and grab that. Okay. So we've got everything that we need except the footprints, right? We've got the
Mm-hmm.
schematic done and we need to add footprints to the schematic. And the way that we do that is we go and we double click or you click and hit E on your keyboard and then you go to this footprint row here. And that enables you to pick the footprint. Let's just use through hole resistors because they're the simplest. Like you've seen these before.
Yeah.
And I'll type resistor. And then you see this thing says resistor SMD, so we don't want those, so we can actually like minimize that. And then here's all the through hole resistors. So you start to see all these different sizes. Um, I think that like a standard is one of these like 10 millimeter, like a centimeter. The 10 millimeter is probably telling you the spacing from like one side to the other of this box. You may or may not want to like determine what size resistor you actually need, but let's just pick something standard like this. When it says axial resistor, that's the ones with the color coding on them, like the standard
Oh,
types that you
okay.
see. So these axial resistors, yeah. So if I, and then it tells you the pitch, like the pitch is telling you the distance between the two holes. So this one says that the pitch, if I can make this even, oops. Oh, you can even go in here and measure stuff? Oh, that's really useful. I've never seen that before. Well, it was letting me for a second. I've never done that before. Okay, anyways, so if you want, you can see that the pin pitch is telling you the distance between these two um, pins. And so it says that this one is 10.16 millimeters. Maybe it could also be the case that you already have the parts and you're trying to build the board rather than ordering them. So maybe
Hmm.
you have the part in your hand and you're like, oh, well, let me just measure this. And you see that it's like actually 15 millimeters. So then you're like, okay, I will be better off to choose this one. Like that's completely up to you.
Okay.
So let's just use this one and we'll assign that 15 millimeter pitch to both of these resistors. Footprint 15. Okay. And so now both my resistors, when I click on them, you actually get the footprint to pop up at the bottom of the screen. One second. I'm going to turn my fan on.
Oh, yeah, no worries.
Okay. So we've done the resistors. Now we need to add a footprint for the LEDs. There's a very standard footprint for 5 millimeter LEDs, which are, you've probably seen these before if you've done anything in the lab. It's these basic types of LEDs. Oops. Have you seen these before?
Yeah.
Okay, so this is like your standard 5 millimeter red LED. And there's also another one that's like a 3 millimeter LED, which is much smaller. Let's just use the standard 5 millimeter ones. So if I double click, I go to footprint, and I'm gonna choose, let's just type LED. So they have all these surface mount LEDs again, but we're gonna go with a through hole.
Hmm.
And you want to find the one with the 5 millimeter diameter. So this is LED 3 millimeter. If I keep scrolling, here are all the LED 5 millimeter. So this is the basic footprint for the 5 millimeter LED.
Okay.
And you may be wondering up to this point, like what, and maybe it'll be helpful to actually put that description here, 5 millimeter. You may be wondering, like, how do you choose a footprint when there's so many footprints? Sometimes it's really just a matter of figuring out something that works. There's probably a lot that work, and you just have to find something that works.
Okay.
And so, like, for example, if I go back to this, there were like so many different options for the 5 millimeter LED.
Yeah.
There's like this 5 millimeter LED. This is a 3 pin 5 millimeter LED. So this might be like an LED that has two colors or something, and so they have two anodes and one cathode, so that's another option. Then they have like an RGB version, which has 4 pins. So there's all these other options. This is clear, this is flat top. It doesn't really matter. They're all the same. So like you can figure out something that works for you. And if you weren't 100% sure, you can go to the footprint editor and actually open up this part and make measurements. So like, let's
Oh.
say I'm not 100% sure about this LED 5 millimeter. Let's say
Mhm.
I don't even know if the holes are big enough to fit the legs of the part. I'm gonna go and just take a pause and I'll save my schematic. I should be saving periodically anyways. And I'll close it. And I'm gonna go to the footprint editor. And I'm interested in looking at that 5 millimeter LED part and I just want to make some measurements. So if I come over to this footprint editor, I can type LED. And again, I'll minimize the SMD ones and I'll scroll to the 5 millimeter one. And now this is that same footprint that we were just looking at.
Hmm.
And now you can actually click on stuff in here and you can figure out what the size of these things are. So like, let's find out the size of this hole. If I hit, similarly to earlier, if I hit E on my keyboard, that will bring up the parameters of that hole. And so it tells me that the diameter of the hole, like the actual pad, is 1.8 millimeters, and the diameter of the hole is zero point 0.9 millimeters. So as long as my leg for my LED is smaller than zero point 0.9 millimeters, it'll fit no problem. Does that make sense?
Yes.
Okay, so then we say, okay, that's perfect. My LED fits. I'm happy with this part. Let me just check one more time the pitch of these pads. Okay, so the pitch is 2.54, and then if I had to guess, the 5 is probably like the total diameter of this thing. Okay. maybe it's like from center to center. I don't know what they specify as the 5 millimeters, but you can make all the measurements that you want and you can see what the footprint is made of. You can also make modifications. I think that the built-in parts don't let you change things, but you can always like duplicate the footprint and add it to your custom library, and then you can make changes to the copy.
Okay.
So if you like wanted to add something to this footprint that says like instead of just having this flat line to indicate that that's the plus or the negative terminal, you could put like a minus sign. You could do all that if you wanted to. Like you have the option to duplicate the footprint and then edit the copy.
Okay. Sounds good.
Okay, so we're happy with this 5 millimeter footprint. I'm gonna close this. I'm not gonna make any changes. I'll go back to my schematic. And now I already assigned it for the green LED. I'll assign the same for the red LED. Okay, LED 5 millimeters, good. And then, like I said, I'll just change my description to include that it's a 5 millimeter LED. Very common mistakes in PCB designs are like you make a footprint for a 5 millimeter part, but then you only order a 3 millimeter LED or something, and then it doesn't fit, or you have to like hack it to make it fit. So the more you do design, the more of those mistakes that you'll probably make and you'll learn from, and then you iteratively become better and better at avoiding those mistakes. That's
Mhm.
why I would add things like details to the schematic as much as possible, like without cluttering it, just because it's good to keep in mind when you're going to be ordering parts so that you don't forget like what you wanted.
Yeah.
That because that's really common for things like especially when you start working in like a company and you're sharing schematics, like it's really important that your schematics are like readable and that you could hand them theoretically to like the next intern to walk in and they could know exactly what you were trying to do.
Sounds
Okay.
good. Be as detailed and thorough as possible to help your future self.
Yeah, exactly. Like you're gonna thank yourself when you order this board and then you go and take a vacation and then you come back a week later and you have to build the board and you're like, what the heck was I thinking when I did this LED? Or like, why did I choose to make this? Like it's helpful to leave yourself notes. You can also leave little notes on the schematic. I think if you just do text, sometimes I'll leave myself notes like, this LED cannot exceed 2 volts or something. And I'll just leave
Mhm.
myself a little note so that I just don't forget. Something like that.
Okay.
Okay. So that's up to you. And then, okay, we've done almost everything. The last thing we need to do is we need to do this connector. So the connector itself also needs a footprint. Have you used headers before? They're like the little black, I'll show you what they look like. You've probably used
Okay.
them before. These things.
Mm, I don't see it. Oh, there we go. No, I have not.
Okay, so these are called header pins and they're really, really common. Um, for like plugging things in because they make these little they're called like they're like male and female headers and then they make male and female jumper wires. If you look up
I've seen the
female
jumper wires, so the headers would just literally be the heads of the wires.
yeah, so the headers are like shaped such that these little connectors just pop right on.
Oh, okay.
So if you wanted to power your board from an Arduino, for example, let's say you had an Arduino close by and you wanted to power it, you could just take a jumper wire from the 5 volt pin of the Arduino over to your header that you're putting on your PCB, and it will make a secure connection there.
Okay.
Okay, so that's one option for the connector. You can also do things called screw terminals. So if you look up like a 2 pin screw terminal. It's like these little things, and you put this on your board, and you can physically stick 2 wires into it, and then you can screw it closed so that it clamps down on the wire.
Okay.
So there's all kinds of ways that you can get like power into your board. There's all different kinds of connections. So it really depends on what you want to do.
Mm-hmm.
Um, for the sake of simplicity, let's just stick with the headers for now.
Sounds good.
I'm gonna go footprint, and then if you go to header, it'll come up. It's like a very common thing, pin headers, and you can see them over here. They have horizontal and vertical types. The vertical ones make sense if you're trying to just stick those wires on top.
Mhm.
The horizontal ones might make sense if you have like they make these 90-degree headers. Let me show you those two just while we're at it.
Okay.
Um, these things. So it like sticks off the side of your PCB if you wanted to make a horizontal connection rather than a vertical connection, which might be good if you're trying to do something that's like low profile and like you don't want the wires to like bend or something. So there's all these different options. Like you'll see as you go through KiCad and you see some of these parts, you'll probably discover a lot of stuff where you're just like, what is that for? And it's almost always because there's some engineering reason why you might want that option over something else.
Yeah, for very specific reasons.
Yeah, exactly. So for those, it's like if you wanted, instead of putting the wires vertically, you just want to stick them into the side of the board, then you have that option. But I'm going to just use a standard vertical. Also, the standard spacing matters. These say that the pitch is 1 millimeter. The standard ones are 2.54 millimeters. Those are the spacing that you
Okay.
have on like an Arduino. So like I'm going to scroll until I find the 2.54 millimeter pitch because that's the standard. Okay. And then I'll just do a 1 by 2. And they have all these different ones. Like you can do 1 by 2, 1 by 3. Uh, like if you wanted 3 pins, you can do that. Like let's say I wanted 2 grounds and 1 power pin, that you can do that, or whatever you want to do. If you wanted a plus, a minus, and a ground, you can use a 3 pin. But we did a 2 pin in the schematic, so let's just stick with a 2 pin. And I'll just say okay. And we have now completed the schematic design of this system, this very basic circuit. We've got our connector and its footprint. We've got our two resistors and their footprint. We've got our two LEDs and their footprint. Okay.
Yeah.
So you would save, and then theoretically, you can do something called a design rule check. I think you have to do inspect. Oh, electrical rules checker. And you just say run. And oh boy, what is it giving me errors for? Off grid. So some of these things really don't matter, but it's probably got something to do with the fact that, you know what? I gotta be completely honest with you. I don't use the rule checker very often, but you're supposed to. It's like a standard thing that you're supposed to do.
Okay.
I feel like I'm confident enough that I don't need to check it very often anymore.
Mm-hmm.
But typically all you care about are errors. You don't actually care about the warnings because the warnings are things like this is telling me that it's not connecting to the grid on the schematic window. That doesn't matter. That's not an electrical issue. That's why it's not an error. It's just giving me a warning.
Okay.
Okay, so I could ignore all those and just see my error. This is telling me that I have a ground pin, but I don't have any power pins. That's not
Mm.
super important either because I could fix that by adding, like, you know how I went over here and added a power label for ground? I could also add a power label for our plus. So if I wanted to do like plus VDC, for example, and just stick that on here, I think it would probably get rid of that error. It's just saying that like we're expecting to see you have some power if you have a ground somewhere, but it's not a super important thing. And
Okay.
you don't, let me just specify, you don't need to do the electrical rules checker in order to move on to the PCB. It's just good practice to make sure that you didn't make any egregious mistakes.
Makes
It
sense.
might throw some errors and you can choose to fix them or not fix them if you want. Like I think if you have like a floating pin, for example, like if I delete this, it will probably tell me that I have a floating pin. And when you get to be doing more and more advanced circuit boards, it's very common to just like miss little things like that. So let's see
Hmm.
what happens if I run the rules checker now. Yeah, so now I have an error that's telling me that this pin is not connected, for example. So that's like a good thing to note. I'd be like, oh, okay, crap, I actually did need that connected here. So I'll
Yeah.
make that change and then I'll say run again, and then that error will be gone.
Nice.
But now I have a new error. My new error is because I have this thing called plus VDC, and I also named this net something else. So the same
Mm.
way I got rid of the V minus in place of the ground, I guess I'll just get rid of the V plus. And let me run this again. I don't know what the deal is with this input power pin. Very interesting. Oh, you know what? Okay, there's this weird thing that KiCad does that if you're gonna use a power pin, you
Mm-hmm.
have to label it by using something called a power flag. I don't
Okay.
understand this very well at all, but it will get rid of the error. If you make a copy of your VDC and a copy of your ground, this has nothing to do with the PCB. It literally just makes KiCad happy. Um, Let me make sure I can find the power flags. It might be in here. How do I do yeah, power flag. Okay. You have to just attach a power flag to both of these things. Again, I don't know why, but this is like KiCad's way of telling you that, yeah, I'm not even going to pretend to understand why I know. I don't know why it does this, but if you do this, I'm certain it will fix the error. So I have these two power flags now. I've basically told KiCad that these are the two things I'm going to use as my power symbols. And now I
Mhm.
believe if I run the rule checker, it will just not have any errors. At
And
least
that's all optional, right? Like it's not necessary for the board for
it's
it to
not.
work.
It's not
Okay.
necessary. This is literally just like I think as best practice, I shouldn't teach you how to do PCBs and just leave errors in my board. But if I didn't do this, it wouldn't change anything about the circuit board.
Okay.
So while it's best practice to eliminate errors, it's not a huge deal, and warnings really don't matter. These are just telling me like various things about how I connected stuff to the grid, like it's off the grid or something, and I honestly just don't care. Like it doesn't make a difference. So,
Okay.
so now this schematic is done. There's no errors, and we're happy with it. And we can say, okay, let's go to the PCB editor. Okay.
Sounds good.
By default, nothing will be here. You need to actually hit this update PCB from schematic, and then that will
Okay.
bring everything from the PCB in or into the from the schematic into the PCB. So I hit update PCB from schematic. It's going to tell me what it's trying to add. This is all not super important, but it's just saying, here's all the things I'm going to do. And you say, okay, it had no errors, and you close. And now here are all the parts. This is what I was talking about. When you first bring them in, it brings all the footprints in for you, and you see the rat lines. Okay, so you can
Mhm.
see, okay, it's expecting this to be connected over here, this to be connected over here, blah, blah, blah. Okay. So what I typically do, there are all sorts of different design methodologies that you can follow. You could try to make it look like your schematic. I think when I first started doing PCB design, I just wanted it to look like my schematic because it was easier for me to see.
Mhm.
Or you can try and make it as compact as possible. And what I do almost always now is I start by just putting things that are going to be connected next to each other. So I
Okay.
see that this is VDC, VDC, VDC. So I'm just going to bring this over here. And now all three of those connections are going to be right there.
Okay.
Okay.
So the rat tails practically just simulate the connection between things?
Exactly. They're just letting
Okay.
you know what things are supposed to be connected and they won't disappear until you've made the correct connections.
Okay.
So if I connect this here, then that line goes away. And then
Okay.
there's one here. If I connect this up here, then that line also goes away. And once you've eliminated all the lines, that means you're done.
Okay.
Okay. So do you want this to look more like the schematic? Like, do you think it would help you or do you not really care?
No, no.
Okay.
I don't really care.
Okay. So if you don't care, then I would just probably leave this. Actually, it might be beneficial anyways, just because I have a ground down there to just rotate these. You can just hit R on your keyboard and rotate them. You can also modify the grid to be as thick or as thin as you want for like moving things around. So if I use like a 5 millimeter grid, things are going to be really choppy. Like I can only
Okay.
move them 5 millimeters at a time. But if I
Mm-hmm.
make it like a really small, like a 0.1 millimeter grid, now I have like really fine control over where I can place stuff. Okay.
Okay. More freedom.
Yeah. So let's just go with like a 1 millimeter for now.
Mm-hmm.
I tend to try to like line these up so that you can draw a straight line. That's really all I normally care about.
Mm-hmm.
And then you don't tend to want things overlapping. The gray stuff is something called assembly text. It's not actually going to be part of the PCB. So if you
Okay.
want, you can hide all of that. You can like double click on it and then you can just say show and you can undo it and then it'll just disappear. And it's nice because you'll keep that value there for when you click on the component itself, but you don't have to see it like clogging up your thing.
Okay.
So it's kind of nice you can do that. Okay.
Yes.
Okay, and then my LEDs need to be connected uh to my resistors in series. I'm gonna space them out so that I have the LEDs right next to each other. Okay, everything looks pretty good. And so this is, not bad in terms of how I'm gonna lay out my PCB.
Hmm.
I might choose to like, I don't like that these labels are sideways, for example, so I'll make them upright. And again, the gray text is something that you don't care about. That's not going to show up on your PCB, so you can always hide that.
Okay. But
Uh,
the yellow text will show up.
the yellow text will show up. So if you look over here, the yellow layer is called front silkscreen. You can
Okay.
actually go in and you can hide and show different layers. So like the top, oh, this is really important. So the PCB is by default, it's a two-layer board, which means it has conductive layers on the top and on the bottom of the board. And the top side conductor is called front copper, and the bottom side is called back copper. Okay.
Okay.
So if you look at through-hole components, they will have copper on both the top and the bottom. So if I click on the bottom copper, now you're seeing the bottom, the stuff that is actually on the bottom layer of the PCB in blue, and the stuff that's on the top is in red. If I have here, let me just add a surface mount part just to show you if I added one. Let's do a surface mount resistor. I'm just going to throw it in there and I'll delete it. So here's a surface mount resistor. Okay. It
Okay.
has copper on the front, but when I go to the back, there's nothing there, right? You don't see any blue here. That means that there's only pads on the top and not on the bottom
Okay.
because the surface mount part is either on the top or the bottom. It doesn't go through the board. So that's probably important to keep in mind. You know what? Just for the sake of example, I'm going to go
Hmm.
back to the schematic and I'm going to add one more branch that has a surface mount resistor and a surface mount LED so that we
Okay.
can see that as part of the design too.
Sounds good.
So when you're running this, you can always go back and forth. And if you make changes to the schematic, you can always do update changes and it will pull all your schematic changes into the PCB. So if I go back right now and I make changes to the schematic, it will just pull the changes in whenever I hit that button.
Okay.
So I'll save this for now. I'll close it. And then I'm going to go back to my schematic and let's add one more resistor called R3 and we'll add one more LED. And let's just call this one a blue surface mount LED. What I need to do though is I need to make sure that I go and get the footprints right because right now I still have my original footprints, right? This is that
Mm.
axial resistor. So
Yeah.
I'm going to double click and I'm going to go and change the footprint by going back to the library and I'll just make it a 1206 resistor. So let's type resistor and I'll do a 1206 resistor. That's just a standard size.
Okay.
And then I will do an LED that's also 1206. So the sizes 1206 and like 0805 and 0603, those are very common, like standard sizes for resistors, capacitors, and LEDs that you'll buy in the surface mount, like packages. And
Hmm.
they're just telling you the size of the sides. Like 0603 means that one side is like 60 mils and the other side is 30 mils. And I
Okay.
should specify mils is a very interesting unit that you've probably never heard of because I feel like only PCB people talk about it. Mils are not millimeters. They're very different. Okay. You see how this says mils and this says millimeters?
Yes.
A millimeter is 1,000th of a meter, right? It's
Hmm.
a 1/1000th of a meter. A mil is 1/1000th of an inch. So it is a really, really tiny unit, okay? And so it's an imperial unit. You know, the imperial system is super weird and metric is way better, but it is a very popular thing that you'll see in PCBs. Okay.
Okay.
So even when you look at data sheets, a lot of the times you'll see some stuff written in mils. You just need to keep that in mind. It is not millimeters. It's a massive difference. So if you say, like I've heard so many people get this confused. They think that 5 mils means 5 millimeters. And so then they do something in their board that's 5 mils and then they order it and they're like, what the heck happened? It's so
Oh,
tiny. And it's because that is a really, really, really small unit compared to a millimeter. Okay.
okay.
So just keep that in mind. Um, so I'm gonna go here. Let me just show you. Surface mount package sizes. So this is the thing I was just talking about. If you look at this, it tells you what the size is for the label. So like a 1206, which is what I was just talking about, is
Mm-hmm.
0.12 inches by 0.06 inches, which that's 120 mils by 60 mils. Okay. Uh,
Okay.
that's how these things are labeled. And like 0201 to 1210, those are very common. If you see any board today, almost any Arduino or anything that you're working with, the capacitors and the resistors, they're these types, here. And they're probably 06, 03, 08, 05, or 04, 02. And if you need like higher power stuff, then you start getting to like larger package sizes. But just to let you know that that's what the numbers indicate, it's specifically telling you the dimensions of the part.
Makes sense.
Okay, so we've got the resistor package 1206. Let's get an LED package that's also 1206. So I'm going to go footprint and I'm going to go back up to the surface mount types of LEDs. And now you can see that there are some 1206 LEDs. They tell you which one's the cathode and which one's the anode. So I'll take that and I'll say okay. And now I'm just going to connect this to my schematic. Oops, I went too far. Okay, so we've added this third branch and let's run the electrical rules checker again. Inspect, and I should have no errors still. Yep, we're good. So we save. We close. You don't have to close it either, by the way. You can leave it open, but I'm just doing it to be complete. So I open the PCB and it will be exactly what we had previously. Nothing's changed until I hit this update button. Okay. So right now we don't have the other two parts. I'm gonna hit
Mm-hmm.
update, and what it's gonna say is it's gonna say, okay, I'm telling you right now, I'm adding D3 and R3 to your schematic. And there's no errors, so I say okay, update and I close, and then it gives me D3 and R3.
Nice.
Okay. And so now I will put my resistor, my surface mount resistor, you know, somewhere over here. And I'll put my surface mount LED in series with it. And this will be my Siri started talking. I'm not talking to you, Siri. Okay. So this is everything I need. I haven't made any
Mm-hmm.
connections yet. And oh, I do like these to be upright. That's just a preference. Also, just as a side note, these little labels are called reference designators. They specifically just give you something to refer to so that you know which part is which. Because like typically you won't have resistors that are all the same, right? We already don't. We have R1 and R2, which is going to be like one part that you may have bought, and then R3 is going to be a separate part. So the designators serve as another like level of keeping track of what part is which. Okay.
Okay.
Typically, you'll have something called a bill of materials, which tells you which parts, like it will have the reference designator. Maybe it's like R1, and then it will tell you the part number and the value. And that bill of materials is just like a component list for everything that you have in your PCB. People will refer to it as the BOM, BOM, because it's bill of materials. So you'll probably hear that terminology at some point.
Okay.
And it turns out KiCad actually has an interactive BOM, which is really nice. And I'll show you that later.
Okay.
If you highlight right here, you see how it says generate interactive HTML BOM. It will literally generate a table that shows you on the left side all the parts, and on the right side, it'll show you the PCB. And you can just hover over the name R1 and it will show you where it is in your PCB. It's really, really useful for when you have big boards with lots of parts.
Okay. That's good to keep in mind.
Yeah, it's really, really nice tool. Um, if you're writing something about that right now, I'll just add this. If you go back to the main screen, the way you add that is you have to do it through this content manager. So
Okay.
we've only been up here thus far. This content manager allows you to add like plugins to your KiCad, and you have to actually install the HTML BOM. So you would
Okay.
go and type interactive BOM and then install it, and then it will add it to your KiCad. Okay.
Sounds good.
So mine's already installed, so I can't like show you, but it should be pretty trivial. And then once you install it, it just shows up here on your PCB window. Okay.
Okay.
Okay, so there is one thing that I think is probably the most important thing to do before we route the board. It doesn't actually need to happen in this sequence, but I would tend to do it in this order. And that is I'm going to draw the outline of my PCB because I don't know what shape I want, but I want to make sure this could have come first. I want to point that out. Like, let's say you have a spec that you're trying to meet and you need to get your board to fit within a certain amount of space. You can draw the outline of the board first. I've just
Okay.
done it last. So it really is up to you.
Mhm.
Um, I'm gonna go down here to the material. So again, this window over here shows you all the different layers of the board. So front copper, back copper, and then you have all these other layers like I talked about front silkscreen. If you hide any given one of those layers, you'll see that it just disappears completely from the screen. So if
Mhm.
I hide front copper and back copper, oh, I still have other stuff there. Okay, so you can still see something. But you see, if I hide front copper, it just disappears, and then I end up with a bunch of other stuff. So you can actually hide all kinds of stuff at the same time. I think you can choose to hide all of the layers at once if you wanted to. Maybe not. There's a way to do that, but I don't know how to do it. It doesn't matter. It will make everything disappear. Like, but it's sometimes it's useful if you're just trying to see. Like for example, if I just didn't want to see any of the silk screen, then I can just like mute that layer and I don't have to look at it. It's sometimes it's nice for when you're doing routing, when you're routing the traces together.
Okay.
Okay. So I'm gonna do the board outline, and the way that you do that in KiCad is you specify this layer called Edge.Cuts. So whatever layer I click on is the layer that I'm currently drawing with. So if I clicked on front copper and I came to draw a square, it's drawing a layer of copper. Okay, it's literally drawing a square made out of copper. But if I click Edge.Cuts, KiCad interprets this as the layer that is the outline of your board.
Okay.
Okay, so if I want to make my board just a plain old rectangle, I come and do Edge.Cuts and I can just click the rectangle tool and then I can draw a box around my PCB, enclosing everything in it. And now this is my board outline, and that's basically the 2D view of my board. Once you have drawn this, you can actually go and view the 3D view of your board, which is really nice. Until you draw the edge, you can't do that. But once you've
Okay.
drawn it, you can go view 3D viewer, and it will show you what your board is going to look like.
That's really cool.
Yeah, it's awesome. And so this it so happens that the resistors and LEDs that we pick don't have built-in 3D models, but the surface mount ones do. So you can see this little surface mount diode and this little surface mount resistor. If
Hmm.
you wanted to, you can go and find 3D models online, and you can add them to the thing. All you have
Oh.
to do is click on LED,
Mhm.
or for example, and then you just go to 3D models, and oh, they do have it. Why is it not showing up? What? It's literally here. That's weird. I don't know why they're not there.
Huh.
Oh, I removed through-hole models. Oh, did
Oh,
that way earlier. Okay, there's everything. So there's your two resistors, your two LEDs, your headers, and everything is here. And this is, to me, it's just fun because it looks really cool. And
that's
you can
so.
be like, look at this board that I designed, and you don't even have it in your hand yet, but you know exactly what it's going to look like. So
Yeah, that's
I love
awesome.
the 3D models. Like if these parts didn't have 3D models, I will go fishing for the 3D models and I'll put them into the board. And if you have you done any CAD,
No.
like any like 3D modeling before?
Mm-mm.
So that's a really useful tool to learn too, like just if you want on your own. Like that's a
Mhm.
mechanical engineering principle. Most EE people don't do CAD, but
Yeah.
if you can do CAD, then it just makes you even more valuable. I love doing CAD, and there's a software called Fusion 360. You can write that down. It's available for Windows and Mac,
Okay.
and you can I think students get a free license. And
Okay. I'll
they have
definitely look into that after the call.
Yeah, yeah, totally. It has great tutorials on YouTube. You can find them. It's made by Autodesk. They make a lot of good software. The big software that everyone uses in the industry is called SolidWorks. I don't know if you've ever heard of it.
Yeah. Yeah.
So Fusion does the same stuff SolidWorks does, but they have a free student version. So if you are a student, I'm almost certain you can go and just make an account and download Fusion. It's also web-based, which is really nice. So it's like everything is stored in the cloud, so you can just log into your account anywhere and access all your files, where SolidWorks is like a
Nice.
desktop app.
Yeah.
But if you ever needed to design a 3D model, that's how you do it. So it's like if you didn't have this LED or you didn't have this resistor and you wanted a model for it, you can do that in Fusion.
Awesome.
Um, I will say this, most of the time, these models already exist. And when you're looking for parts, so we were talking about DigiKey earlier,
Yeah.
you can actually filter. So we were talking about like doing the filters. You can filter by parts that have 3D models. Like you can do that.
Ooh.
So if you come in here, I always do that because I want the models. But
Mm-hmm.
like, don't limit yourself if you're ever doing a design and you're like, dang, this doesn't have a 3D model, so I won't use the part because the part might just be important enough that you need it anyways. But
Mm-hmm.
if you're just doing fun stuff, this thing here, it says EDA/CAD models. I think EDA is like electrical design assistance or electrical design automation, and CAD stands for computer automated design. So that's just telling you that those are 3D models that are going to come with the part. So now I've narrowed my search. Remember it was 11, now it's only 5. If I
Mm-hmm.
apply it, all of those parts now will come with CAD models. So let's just pick this Vishay part because Vishay is a good company. And then you see it says EDA/CAD models. I'll click on
Mm-hmm.
models, and then they'll literally give you, like it's through their manufacturer, the step file, and that is the 3D model file.
Okay.
So if you click
Very
step
cool.
file, you can download that and then you can open it in KiCad. Let's go back. If I wanted to add it, like let's just say that that was for my resistor, I would click here. And then in the 3D models, you can go and add a 3D model. So you could delete the old one, add the new one, and then you just go to files and then you go and navigate to the step file. And then it will just
Okay.
import that model. Okay. So that's an option. It's even better when KiCad already has everything for you because then you don't have to do all that.
Yeah.
Okay, so we're getting close. This is almost done. Now we have to connect everything. Okay, so there are two ways to connect things. I'm going to show you the simplest way to connect things, and then when we're done, I'll show you an alternative way to connect things that's more, I guess, professional. But I didn't do this for a really long time, so don't feel like you have to do it.
Okay.
The easiest way to connect things is just traces. They're called traces or tracks, and that's what I already showed you earlier. It's
Mm-hmm.
just coming and grabbing this little tool here, route single track, and
Mm-hmm.
you can just click pad to pad and just make connections like this. It's very, very easy. Um, I'm gonna change this to a finer grid now that I'm doing traces because uh, you might need to do that. Just to make the routing a little bit like less choppy. Uh,
Okay.
so let's route on the front. I'm gonna route a pad from VDC to this resistor, and then I'll route another pad from VDC to this resistor, and then I'm going to route here. One rule, it's not a hard rule. I'm starting to understand that you don't need to do this, but it's like a good best practice. You want things to connect with 45-degree bends. You don't want 90-degree bends. So like it's a bad idea to do this, for example. My understanding is that it has something to do with when the PCB manufacturers actually make these traces, they have an easier time making 45-degree angles than they do 90. So instead
Mm.
of doing that, you would just make a little elbow that like does something like this, and it's totally fine.
Okay.
That's why you tend to see stuff like this on PCBs more than you see 90-degree angles.
Yeah.
And it's not a hard rule. Like it's not going to cause any errors, and the PCB will probably work. But I've it's been like baked into my brain, so I never do 90-degree angles.
Okay.
Okay, it might come up one day where you end up using 90-degree angles, and it's really not. I don't think it's a problem anymore. My understanding is it was a problem a long time ago, and it's since been like corrected, and the fabrication facilities can handle it now. But best practice is just use this 45 degree. Or I guess in this
Good.
case, it's like a 135-degree angle. Um, you can, once you have the trace drawn, you can drag it to like alter it.
Oh, nice.
So you don't need to keep it exactly how you had it. And if you're just like mad at a trace and you want to undo it and redo it, you can click either segment by segment, like you can go Control Shift and click all the segments, or you can click it and then hit U, and it will select the whole trace, and then you just hit delete, and it'll just delete the trace.
Okay.
Okay, so I'll reroute that. I wanted to show you one other thing with this. Right now, I routed everything on the top layer, but
Mm-hmm.
as I mentioned, through-hole components actually go through the board to the bottom layer. So I don't need to route this connection on the top. I could have routed it on the bottom. So let me show you. If I go to bottom copper, I can actually do a trace on the bottom, and that will also make the connection. And now that trace is on the bottom of my board, not on the top of my board, but the connection is the same.
Okay.
So let me show you what that looks like in the 3D viewer.
Mhm.
You can see I have a trace here that we don't see on the top anymore. It's gone. And then we have a trace here that we can see. But if I go to the bottom of the board, now I have a trace between those two pads.
Oh,
So
and
you
that's
can,
just personal preference.
so it's preference, but it's also, let's say you wanted to put another component here. You could put a component here now.
Oh.
So this is where using surface mount components becomes really, really valuable. If I wanted instead, I could let me erase this trace. I could put my surface mount components like in the middle here, and I could
Mhm.
just put this um, right on top. And there's no problem with that because on the bottom layer, that blue is not doing anything to this resistor, right?
Right.
If I look at this, my resistor is sitting there completely isolated from what's going on the bottom of the board. So it makes compact routing very nice because if you need to route something, you can route it on the bottom of the board rather than routing it on the top. And you can now put components here. Where with a through hole part, as soon as I have a hole here, I can't do anything there. That
Yeah.
space is like fully occupied.
Makes sense.
Okay,
Yeah, it
so
makes it look really neat.
yeah, you can make the whole thing very compact, and then it's nice when um, you can actually go to higher number of layers too. So that's not that's like this is like more maybe we can do like a more advanced session at some point if you want to like go
Yeah.
into more advanced stuff at some point.
Mhm.
But this is a two-layer board. You can actually specify any number of copper layers. So if I go to I want to say it's in file, yeah, board setup. You see that the board stackup that I'm specifying right now, you click on physical stackup and it's asking you how many copper layers do you actually want in your design. All these other layers you don't really have to worry about because the people who build the PCB will basically handle that for you. But you
Mhm.
can specify an enormous number of layers. And so let's just say I click 4. It's going to change everything in my stack up. When it says stack up, it's literally talking about the layers if you were to look at a slice of the PCB. So the very top is the silk screen, which we've talked about. That's the text. And then
Mm-hmm.
you have some of these other layers, which I haven't discussed yet, but they're not super important yet. And then you have a front copper layer, which we've talked about. That's the red. But now you have two inner copper layers. These are actually internal to the PCB. And you can use them to route stuff. You can't obviously put components on those layers because they're inside the board. You can
Mm-hmm.
only put components on the top and the bottom, but you can route traces there. So for making even more compact designs, this gives you even more space to route stuff.
Okay.
So this is like an additional layer of freedom that you can add more copper layers inside the board. One thing I'll say is more layers is more expensive. So when you order a board that's 4 or 6 or 8 layers, it
Mm-hmm.
becomes more and more pricey. So you tend to want to use the fewest number of layers possible. Like if you can do it with 2 layers, do it with 2 layers. But if
Okay.
you need
Sounds good.
4, you can do it with 4, and then that makes your life easier with routing. Like I've done up to 6 layers before.
Mm-hmm.
One of my more recent boards was a 4 layer one, but I've done up to 6, and it makes my life a lot easier if I'm trying to make things really small.
Mm-hmm.
Uh, and but for now, let's just stick with 2 layers. This is like these are things I didn't learn until much later, so I don't want to like overwhelm you. But
Okay.
it's good
Yeah,
to
sounds
just
good.
know like what options you have.
Right.
Okay, so far I've routed my VDC. That's all done. I want to
Mm-hmm.
show you that something that's important. Is that you, babe? I heard the door. Something that's really important is that when you're designing a PCB, you actually do need to consider sometimes, it depends on what the application is, but you need to consider how much current each trace is going to handle. Because really, again, your PCB is really thin, but this copper layer is really thin. Like this thing is like micrometers thick copper.
Mm-hmm.
So there is a limitation to how much current this trace can actually handle. And you need to take that into account when you design your board. Okay. Most of the time, if you're doing low power stuff, you probably don't need to worry about it. But if you are doing like motor driver stuff or like you said something about the CAN bus, that kind of stuff,
Mm-hmm.
if it's like communication, you probably don't need to worry. But if you're dealing with large currents, you do need to worry because the traces, they can get really, really, really hot if you don't design them properly and they can actually break. Okay.
Okay.
So let me show you online. There are all kinds of PCB trace width calculators. So if you just type PCB trace width calculator, you'll find these all over the place. There's all kinds of free ones. And if you're like, okay, I want my current to be uh, 5 amps. That's a lot of current. Let's just say 1 amp. Thickness of copper on a typical PCB design is 1 ounce per square foot. I got to be honest with you, I don't know what this unit means, but it correlates to the thickness of the copper. So one ounce per square foot is thinner than 2 ounce per square foot. And if you do higher thickness, the board gets more expensive because you're using more copper. Okay.
Okay.
So this is asking me how much am I willing to allow my temperature to rise and how long is my trace? So it asks you all these things. So let's just say I don't want it to rise more than 20 degrees Celsius and my trace is like 1 inch long. So this is telling you that I need this trace for this current and this thickness of copper to be at least half a millimeter thick.
Okay.
Okay, so you can use these. These are really easy to find trace width calculators. Some of them will give you more options, some of them will give you less options, but you generally don't have to worry about it. But if you're dealing with higher currents, it's a good thing to keep in mind.
Yeah.
Because look, it's this one says I need a half millimeter. If we look at my trace right now, it is zero point 0.2 millimeters, so it would technically be too thin. So if I
Yeah.
wanted to do zero point 0.5 millimeters, I can change that, and now you see I get a thicker trace.
Okay.
Okay, so you just double click on the trace and you can change the track width to half a millimeter.
Is it common for different traces to be different thicknesses?
Yes, very common.
Okay.
So typically what you'll have is you'll have like on a board where you're dealing with some stuff is like power and other stuff is like basic like communication or logic levels. those things don't need to be thick, but the power stuff does need to be thick. So you'll see big fat traces where you have like the power coming in, and then you'll see really thin traces everywhere else.
Okay.
So super common to see different traces of different thicknesses. Okay, so another thing you can do is you can actually set predefined sizes for your traces. So if I wanted to, I could like set 0.5 millimeters as the default. And then I think every time I route a trace from this point forward, it will allow me to like pick if I want to use the default or if I want to use my custom like decided one. So now they'll all be half a millimeter. You see
Oh,
that it's like much
nice.
thicker now.
Yeah.
Okay. I've made almost every connection except for the grounds.
Hmm.
And now I can connect my grounds together. This board is almost done. Like I said, this is the simplest way to route everything together. And you see that I have no more blue lines. Theoretically, this design is done. So
Hmm.
what I'm going to do is I'm going to say, let's go to inspect, just like we did with the schematic. There's this thing called the design rule checker. It's going to
Okay.
make sure that you don't have any two pads too close together. You don't have any parts that are too close to the edge of the board. Things like this copper going over my silk screen, that will throw a warning, so I'll just move it.
Okay.
It doesn't matter. It actually doesn't matter at all, like electrically, but it will give you a warning.
Hmm.
It might even give me warnings here, like because I have this track going over this silk screen, but those things are irrelevant. What we're really concerned with is like, did we forget to connect anything? Do we have any parts that are overlapping? Like these pink layers are called like the courtyard layer. You can
Okay.
see that there's this, or yeah, this courtyard layer. It's telling you like that is the amount of space that the part is likely to take up. So you don't want to put another part inside of that box. So like if you were to try to move this resistor really close over here, you see how it like shows up like red? It's saying
Yes.
like, yeah, you don't want to do that. And then if like, it's nice that KiCad has that now where like there's this kind of active DRC where it will throw errors as you're working rather than having to wait till the end. But when you
Yeah.
are done, it's a good idea to do the DRC, the design rule checker. You run it. I should have no errors. I have no errors, no warnings. That's fantastic. That means my board is done. I could order this board right now. Okay, so let's just, for one more time, let's just go and look at the 3D viewer. And so I've got my traces. You can see them. I've got one on the bottom. You can see like the holes coming out of the bottom, stuff
Hmm.
like that. So this would be done. But some other things that you may want to consider when doing a PCB, you might want to add
Hmm.
holes to the corners so that you can mount this somewhere. That's like an option. You can add holes to the corners. You can add text. So like, let's say that you wanted to put your name on this PCB. Let me I'm gonna switch this trace so that it's on the bottom of the board so that we can put your name right here.
Okay.
So I'll just route this on the bottom. You see this little ugly elbow? You can fix that.
Yeah.
I like went too far. You can just fix it by like dragging this around until it, oh boy. Can you? You should be. Bro. Oh, it's because I have this extra little, yeah, okay.
Oh, that makes sense.
Oh my
Ooh.
gosh. This happens often and you just have to like mess with it until it behaves. There it goes.
Yeah. Just a
Okay.
small inconvenience.
Yeah, yeah. Okay, so then if you want to add text, like I talked about, there's this thing called front silk screen.
Hmm.
You click on front silk screen and then you go text and you might just say Natalie N 2026 or something. And it'll give you this little silk screen label. And you could like put that here, for example. And then you go look at the 3D viewer and you can see it. So now that's on the board.
That's really cool.
Yep. And then you can add like logos and stuff too, which is really cool. Like I added a Stanford logo to one of my boards.
Oh
The
yeah, you showed it to me. I saw it on the corner. I thought that was really neat.
Oh yeah, okay, yeah. So that that is there's an interesting way to do that. So there are like all these other tools that I had showed you previously in the KiCad window that we didn't talk about. One of them is called the image converter.
Mhm.
So in the image converter, let's say you wanted to put like your favorite logo or something that you wanted, your school logo on the PCB. You can go and find like a UNR logo. You want it to be, I think PNG is honestly fine. You can download this. Let's just save image as. I'll download it to my downloads and I'll just say UNR logo. You need the thing to be in the bitmap format in order for it to work in KiCad. So if you see this thing, it says convert bitmap images to schematic symbols. So I
Mhm.
downloaded it as a PNG. You're gonna need to come and do like a PNG to BMP convert. I don't know if you've used like file converters like this before.
Yeah.
So this like cloud convert does pretty much everything that you could ever need. I can't even believe how good it is and it's free. So if you want, you can just throw this PNG that we just downloaded into the cloud convert thing. We convert it and then we download it. And now we have our bitmap. We can go back into this is all just fun stuff. Like you don't act you, this is
Yeah.
obviously not necessary, but like you go
Just
into the
extra.
what's that?
Just extra stuff for fun.
Yeah, just I love it. Like once you're done with your PCB, it's like a work of art and you just want to throw something in there.
Yeah.
So if you open the bitmap image, there it is. I think you can, yes, you want to make it a footprint
Mhm.
and you want it to be on the front silkscreen layer, for example. That's like what we want. We're going to put it on the silkscreen. So if I say export to clipboard, I'm pretty sure it will literally just put it on my clipboard and I can just paste it. There it is.
Nice.
So one thing is you might have to manipulate the size of this
Mm.
thing. I think this is way too big.
Yeah.
So let me go back. You can decide the size that you want right here. So if I go into my KiCad thing, let's say I only have this room down here in the corner for it.
Mhm.
I'll go measure that. So I'll just put a box here. This is like 5 by 5. So I'll just tell it to export 5 by 5, or it'll lock the ratio. So let's just do 5 by 3.8. Export to clipboard. And now when I paste it, oh, that's way too tiny. It's probably taking something around it too that I haven't accounted for. So let's do
Oh,
15 and see what that looks like. There's some like guess and check here. I'm sure there's a better way to do this. That's good. Okay. And then the other thing is like there's like the little reference designator that we don't care about. We can just hide that and then you'll get like the nice logo.
that's really cool.
Yeah, it's so cool. So you save and then now if you go to the 3D viewer, there will be a little Reno logo on your thing.
Oh, nice.
Yeah. So this is pretty much everything that you need to know. But now I'm going to show you how you actually go about ordering the board.
Okay.
So everything is done. We're happy with this PCB. We've saved it. Uh, you now need to export the files that you need for fabrication. Okay. These
Mhm.
files that you need for fabrication. Okay, let's just recap. We designed the schematic.
Mhm.
We assigned footprints to all the parts in the schematic. We uploaded the schematic to the PCB editor. All the footprints were here. Then we connected everything together. We gave the board an outline and we did the DRC. That's the whole process. The final step is ordering the board. Does everything like up to this point make pretty much make sense to you?
Yeah. Yeah.
Okay, great. So the the outputs that you need when you're going to order the board are called Gerber files. You can write that down. Gerber files.
Okay.
Okay. So when I'm ready to order my board, I go File and I go Fabrication Outputs. And you see this thing says Gerbers.
Yes.
You click that. And it brings up this menu of all the different file types that you can add to your export. What we need to tell the people who are building this board is we need the copper layers. It's already
Hmm.
got everything checked that you need, so you actually don't need to make any changes, which is really nice. But let me now tell you what some of these other layers actually do so that you understand why they're checked. So the front and the back copper should be obvious. That's where all of the pads are actually at.
Hmm.
The way that a PCB is actually manufactured is that the entire board starts out as copper. It's like copper, and then there's a layer of insulator, and then there's another layer of copper. And what they do when you tell them, this is my board, is they actually go and they etch the copper away everywhere that you don't have it.
Oh.
Okay. So it would be all copper, and then you tell them, I'm going to etch away all of this other stuff that's not copper. And so a
Hmm.
lot of the copper just gets discarded, and only the copper that you want is what actually gets left behind. Okay.
Okay.
This layer that's called front mask, it tells them so after they remove all the copper that you want,
Hmm.
or they remove all the copper you don't want, and they leave behind the copper that you do want, they apply this layer called solder mask. And if you look at the PCB on our 3D viewer, you can see that there's copper that's exposed, this yellow stuff, and then there's
Hmm.
copper that's kind of buried, right? Those are both on the top copper layer, but one of them is covered in solder mask and one of them is not. Okay. So when you are ordering a PCB, a lot of the footprints and stuff that you have by default, they've already done this thing called removing the solder mask layer. Okay. So the solder mask would by default, it would cover up all of the copper because they apply that to the whole board unless you specify, I don't want solder mask here. And all of the footprints that we looked at up to this point, they had already removed that solder mask. So let me show you if we go into the footprint editor again, and we'll go to the 1206 resistor just as an example.
Hmm.
So let me open up the 1206, or let me just type resistor 1206. Okay, so when I remove the front copper layer, you can see that there's still this layer here. That is the mask layer. And that is them telling you that we want to remove the solder mask from this region. Okay.
Okay.
So it makes sense that anytime you're going to be soldering a component onto the board, you need to remove the solder mask because the solder mask is there to protect the other copper from getting hit with solder. So when we're actually going to do soldering, they want to know where are you going to be soldering and we'll remove the mask for you. But it's
Okay.
important to note that these footprints that come built in, they have that layer already removed because it's very common for someone to go and make a custom footprint, like you're going to make your own. And you're
Hmm.
like, okay, I know I need front copper, but you forget to add this mask layer. Because if you don't add this, like this is the mask, this is the whole pad. It's got front mask and front paste and front copper. Those are all of the things that are there.
Okay.
If you don't add the mask layer, so I'm going to remove that just for now. Um, Let me see what happens. So if I don't add the mask layer, I want to see if I can look at the 3D. Oh, I can't save this, but let's see if I can look at the 3D viewer. You see how now there's no exposed copper there? The copper
Yes.
is actually buried beneath the solder mask layer. So you, the user, would not be able to solder to this pad.
Okay.
Okay. So by default, I'm just telling you this because it's really important for when you do custom parts. By
Hmm.
default, all of these parts, the people who have designed them have already taken into account that you need to remove the solder mask layer. And it's sort of counterintuitive because when you're putting like front copper or back copper, you're adding something to the board. But when you put the front mask layer, you're actually telling them where you want to remove something from the board.
Yeah.
Okay, so that's how that works. Like anywhere where you put the front mask layer, that's telling them I want to remove the copper. Okay. And one other thing that I can probably do to drive this point home is I can show you, we can actually add a little front mask on our board here. Let me just draw a little region of front mask. and it will remove the mask from our trace, and then you'll see like a little exposed piece of the trace.
Okay.
So let's do draw filled zones, and then I will choose front mask, and then I'm just gonna draw a little region here of expose. This is me saying I want you to remove the solder mask from just this little region. Okay.
Hmm.
So now I hit save and I go to view 3D viewer. Wait, what? Oh, you know what? Hold on. Okay. Once you draw a zone, you have to hit B on the keyboard for it to actually activate that zone. So
Okay.
that's not important right now, but just that's why that didn't work. If I go to here now, look at this. So they've actually cut out that mask layer, and you're seeing now this region of like bare copper. Does
Hmm.
that make sense?
Yes.
So on all the parts, that's been done to the exact specifications of the pad, so that exactly where the solder pad is, there's no solder mask.
Okay. That makes sense.
Okay. Okay, good. So that's why we need the solder mask layer in the Gerbers. That's what I'm getting at, the point that if you don't add that, then they don't know where do you actually want exposed copper versus where do you want unexposed copper.
Hmm.
Okay. So that's super important. Okay. The other thing that was in there were the paste layers. So front and back paste. These are less important, but if you look when I come down here and I click on front paste, it puts like a little gray box here.
Hmm.
When you're building, and I think I covered this in Module 5, when you're building electronics, a lot of the time you have an assembly line that's doing this building, and
Hmm.
the paste layer actually tells them where you're going to apply solder paste. So
Okay.
it's only on the surface mount pads. You can see that there's no other pads on here that have paste. It's only the four surface mount pads because typically you only use solder paste on surface mount parts.
Okay.
But the paste layer is important to specify for the manufacturer to know where you're going to be putting paste because I mentioned that there's this thing. Did I mention in Module 5 that there's this thing called a stencil? Um,
No.
so when you do solder paste application, let me show you this. A stencil is a metal sheet that has cutouts in it everywhere where you want paste to go.
Okay.
So you take this thing and you just wipe paste all over the stencil, and then the paste only goes through the holes. And so theoretically, you would apply the paste, and then you would wind up with paste not anywhere on your PCB, but only on the surface mount pads. Does that make? And then that's where the parts go, and then they get soldered. Does that make sense?
Okay. Yeah, that makes sense.
So when you're telling the fabrication people, I want this solder mask layer, like we have these gray squares, that
Hmm.
lets them know if they're going to be making the stencil, they're going to cut these holes out in the stencil so that when you put your stencil down, that will actually be where the paste will go. So the just to like fill in the gaps of like what some of these layers are that we're adding to the Gerber so that it's not magic. You don't need to worry too much about this, but just so that you know. So okay, let's go back to file, fabrication outputs, Gerbers. And so you see they have front and back copper, front and back paste. So you want the paste on both sides because you could have parts on either side. Front and
Okay.
back silk screen, of course, because you could have text on the front or the back. Front
Hmm.
and back mask because you could have parts where you want the mask removed on either side. And then the edge cuts, which is that's the outline of the board.
Okay.
Those are all the things you need for the Gerbers, okay? So I'm gonna hit plot. And what that does is it just generated those 9 files. There are 9 files that we're going to send to the people that are building the board. And I'll show you where they all went. Okay.
Okay.
So the first step is generating the Gerbers. There should be 9 of them for a 2-layer board.
Hmm.
If we're going to do through-hole parts, which almost every board will have at least some through-hole parts, you also
Hmm.
need to generate drill files. So you see this thing that says
Okay.
generate drill files?
Yes.
So you say generate drill files. There are different types. To be completely honest, I don't think it matters a whole lot which ones you choose, but let's just choose Exelon, I think is the default one. And there are 2 different types of holes. It specifies those. So we're just not going to mess with any of these settings. We're just going to hit
Hmm.
generate. and then we're going to
Okay.
close this. Okay, so we've done all of the file generation, and if we go look now at our KiCad project, there's a boatload of files in here, right? These weren't here before. It was just the schematic and the PCB. Now there's all of these
Mhm.
other files. Okay, so if you go navigate in your computer to where this thing is stored, so for me, it's stored in Documents, KiCad. It's very important to keep track of where these things are, by the way.
Yeah.
Projects, and I have Natalie example. So here are all those files. So I would go now and I would organize this by type. I've got my 9 files, right? Gerber,
Mhm.
Gerber, 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 Gerber. The job
Mhm.
file is telling it which Gerbers you want. That's not something you need to send to the fab. You only need the ones that are actually Gerber files. And then
Okay.
you have the 2 drill files. It generates PTH is plated through hole and NPTH is non-plated through hole. They're just two
Okay.
different types of holes. I guess the fab like processes them differently. So you would control and select all those things. So you have everything you need now. You right click and you would just zip this up, send to a compressed zip folder. And I would just call it Natalie example Gerbers. Okay, this folder is all you need to send to the fab. So I'm going to show you how that works now. So one of the fabs that we use that's really cheap, it's in China. It's gotten more expensive because it's in China and there's like tariffs and things now, but it's called
Yes.
JLC PCB. Okay. You can order from the US also. There are other fabs, but stuff from the US is very expensive typically. If you're
Yeah.
only doing 2-layer boards, there's one in the US called Oshpark, if you want to check that out. They will make PCBs for you, but they have to be purple. They don't let you specify the color. It's just purple. That's like their thing.
Oh,
They're pretty cool. I think they're really nice. And they're cheap and they're US, so they come quickly.
okay.
You can poke around Osh Park and see if you want to order, like if you were going to order a board, you could order from them. We order
Hmm.
almost everything from JLC PCB in my lab.
Okay.
That's from China. And then one other place that you can look at is called PCB Way. So not to give you too many options, but JLC and PCB Way are almost exactly the same. JLC is a little cheaper, so we use JLC. They're very, very similar interfaces. So I'll just go through JLC to show you how it works. But if you
Okay.
wanted to just order something from the US, you can also order from Oshpark. And you see how it says browse for files? Everyone's
Yes.
waiting for your Gerbers. So they're like, send us your Gerber file and then we'll get started building your thing. So that's what this means. So
Okay.
I'm going to close Oshpark. I'm going to close PCB Way and I'm just going to do JLC. So even before you design a board, JLC will ask you for like a rough size, and they can give you a quote right away. That's kind of nice.
Oh, nice.
So ours is a 2-layer board. Let's just measure the dimensions really quickly. You can do user drawings, and then it'll just draw it on there, but it doesn't affect anything. Okay, so that's 29 millimeters. Also, I know I'm in millimeters because it says it over here.
Okay.
You can change to inches or mils if you prefer. 29 by 32. Okay, so that's the size of our board. So I would
Hmm.
go to here and I would say 29 by 32. It's actually not going to matter because we're going to upload the file and they'll extract that information from the file.
Okay.
But let's just do get instant quote. You have to order a quantity of 5 minimum, which is unfortunate, but that's because they do mass production. So you can't
Makes
order
sense.
like just one board. You can
Mm.
order any number of enormous amounts of boards, but you can't order less than
Gosh.
5.
Yeah.
Okay, so you'll see that this is incredibly cheap. Uh, $2 is the calculated price, and then it's like $27 to ship because it's coming from China. So the bulk of the cost is actually the shipping.
Mm.
As you add features to the board, like if like FR4, that's the base material that's like between the two copper layers. That's the cheapest one. There's all these other types that are way more expensive, and you don't need to worry about those until you're doing more advanced stuff. But like, let's just say I click Rogers, you'll see the price skyrocket.
Oh, yeah.
Yeah. So FR4 is good for most stuff. Like you don't need to worry to go beyond FR4 unless you're doing something very special.
Okay.
Okay, so FR4 is fine. We know it's 2 layers. We know the dimensions. We're gonna buy 5 because that's just what we're doing. And then they just give you all these options. You don't have to worry about a ton of these, but we'll just go through them so I can show you. Um, Rounded edges is really nice. It seems like it doesn't add to the cost, but then you won't get like really sharp edges on your board. They'll just go
Mm.
and like round them when they create the board because we made it a square. You can
Okay.
also round them in KiCad. There's a way to do that, but we don't need to worry about that right now.
Hmm.
Different designs. You don't have to worry about this. This is for people who are trying to make multiple different boards and putting them all on the same panel. Because when JLC does stuff, you can actually add multiple different designs to the same panel and then they'll fabricate them together. But if you're just ordering one, you don't have to worry about that.
Okay.
Delivery format is just them asking if you want them to deliver it to you as a panel. So like all the boards are like in rows and columns and they haven't been broken yet. You don't usually want that. You just want them to send you the single PCB because
Okay.
that means that they've just broken them up and put them in a package for you and they're ready to go. So all these things are like default settings that you don't have to worry too much about. And I don't want to like overwhelm you, but you can select the thickness of your board. 1.6 is standard. You can make it thicker or thinner. That actually changes the cost. So if we go like super thin, you'll see that the cost will go way up. If we go thick, the cost also goes way up. But if we just use the default, it's cheap. Uh,
Yeah.
oh, for some reason they added something now. Oh, because I changed something and then it changed another setting. So something that's weird about this is that if you like I changed it to zero point 0.4, it came down here and since ENIG is the only option for that setting, it doesn't have these options. When I go back to 1.6, it keeps this checked. So if you do that, you want to go back to like the cheapest option and then you'll go back to the cheapest price.
Okay.
Okay. You may want to go lead free. That's a good, health thing. I think
Hmm.
we work with lead all the time. It's not a huge deal. But if you do lead free, that's going to add a little bit of cost. That's fine. ENIG is like this thing called immersion nickel gold. It's like a very high quality finish on the pads that make them easier to solder to.
Oh,
Not
okay.
necessary, but it's an option. So like that
Hmm.
makes the price go up too, but you don't need that.
Okay.
PCB color, green is the quickest. You'll see that like if you want one of these other colors, it says it takes 2 more days. That's fine, honestly. I don't really care usually because sometimes I like to have like a fancy color, but if I'm just trying to get
Hmm.
it back quickly, I would just go green.
Okay.
You can pick any of these colors. And then down here, a lot of this stuff you probably just don't need to worry too much about. Um, Let me just look and see if there's anything important. You can generally stay with the default settings unless you know that you want to change something.
Okay.
Like for example, like I was talking about earlier, the copper weight makes a
Hmm.
difference with how much current the traces can handle. So if you wanted thicker copper, you click 2 ounce and that'll also make the price go up. So you see that like changing the default settings generally just changes the price. So for very basic things, you typically don't have to change a whole lot of stuff. And you can also hover over any of these things and they tell you what it means.
That's cool.
So yeah, so
Yeah.
anything that you're interested in, like what the heck are they talking about with confirm production file? You just hover and then they have a little description of what that means.
Oh,
Okay.
nice.
So we're at the part now where this is just like we've done the basic, like we put in our dimensions, but now we actually have to add our Gerber files. You can do that first, and then select all the settings.
Hmm.
So I'm gonna go add Gerber file, and then I'm gonna go back to where I had that saved. It's in Documents, KiCad 9, and then inside Projects, Natalie example, and then I have my zip file that I made, right? That's my Gerbers. So I say open,
Yeah.
and now they're uploading the files. And so it'll complete at some point, and then I think they'll even show you a model of what your board is going to look like because they have like a Gerber viewer that's really cool.
Oh, that's
Um,
sick.
Let me see if we get to the point where we save it to the cart, if it'll actually show us. So it says it detected a two-layer board, so they detected how many layers we had, and it
Hmm.
detected 29 by 32 for our dimensions, which is what we told them.
Yeah.
And so if you didn't have these things put in, it will autofill those in for you. So let's say we're happy with everything. You want a blue PCB, you're happy with all the default settings, and then you just say save to cart. Oh, it's going to make me sign in. You will probably want to make an account, but you can always continue as a guest if you want to.
Hmm.
Making an account is good because then it'll store all of your orders in okay, so yeah, now it's showing us
Oh,
the board.
nice.
So there's your blue Reno board that you can, order. And this is like a rough idea of what it's going to look like. This is
Hmm.
really nice because this could be where it shows you, oh, wait, that R3 pad is not uncovered. What did I do? Let me go back and make a change to my Gerber file. Right?
Yeah.
Because it's like, oh, I thought that that would be solderable, but actually it's showing up as covered. So let me change that.
Okay.
So this is ready. Like you literally can save this to the cart now, and then you can just purchase it. You go to view cart. Sometimes they'll do this thing where they review your production file. That was one of the settings. Like you can ask them to do that. But if you're ready, you could just click, and then I guess they're doing some special offer right now. I don't know what that's all about, but like you would say secure checkout, and then you would just go and order your thing.
That's really
That's
nice.
how it
Yeah.
works. So that's the whole process from beginning to end. And it's obviously, like I said, like the shipping is like the entire cost because it's coming from China.
Yeah.
So if you want to do an order, I maybe would recommend just doing it through Park so that the shipping is cheaper. But you might see that Park also costs like $50 total. And then even with $40 of shipping, JLC is still cheaper. So
Mm.
you can weigh your options.
Okay. Yeah. Sounds good.
Mm. There was one other thing I wanted to show you
Okay.
before we get off here. Do you have any questions?
No, no. It was all really straightforward. You explained it very well.
Okay, great. I'm very glad. If any questions come up, you can always just email me.
It's
Um,
good.
so let me show you something that is really important for PCB design. You can it's so there's two things kind of. There are these things called vias, which allow you to tunnel from one layer to another layer through the PCB. So if I'm routing a trace and I can't go all the way across, but I can go part of the way, for example. So like let's say I wanted to go, let me just show you just as an example. If I start on the top layer, I can start routing this trace. And if I hit V on my keyboard, it brings up this little hole. And what it does if I click it is it'll switch me now to the bottom layer of the board. So now
Oh.
it's gone on the top, it's gone through a via, and it's gone to the bottom layer, and it's all still connected. So
Hmm.
now I could connect this here, and then let's say I want to go back to the top. I'll go via again, click, and now I'm back on the top.
That's really cool.
So that those are called vias, and they let you tunnel between layers. They're very, very useful for all kinds of stuff in PCB design. If
Hmm.
we go look at the 3D viewer, you see that it starts on the top, it tunnels through the board, and then it picks up here. It goes on the bottom over to this via, and it's literally like it's just a hole in the board that's like tunneling a conductor through the board. So they actually
Hmm.
plate this hole with copper so that there's like a good connection. And then obviously on the other side, there's another via, and it would come out, and then it finishes that connection right here.
Hmm. That's really interesting.
So yeah, so vias are useful.
Hmm.
And then there's one other thing. So I'm gonna do something. I'm gonna erase
Okay.
all of the ground connections because I want to show you an alternative way that you can make connections. So the first way that I said that we can make connections is using tracks or traces, right?
Hmm.
There's another way that we can make connections, which are called copper pores. And what it does is it will pour copper all over the board and it will make direct connections to your pads and it will just avoid all your other nets. Okay, so it seems kind of weird, but it's a really good thing to do if you need um big connections like with lots of current like I was talking about earlier. And
Okay.
since all of your currents typically return on ground, you normally need a lot of current flowing on ground. So you tend to do stuff like this for ground. So I'm going to show you what it looks like. So I'm going to come here and I'm going to say I want to draw a filled zone and I'm going to pick front copper for that zone. Okay.
Okay.
what it's going to do is it's going to ask me to start drawing here. I'm going to make this a little bit thicker of a thing because you don't need to be perfect on the PCB. You can actually just draw a box around it. So I'm going to start out here, and then it's going to say, what net do you want this copper to be connected to? I
Okay.
want it to be connected to ground. So I'm going to click ground, and I want it to be on the front copper layer. And then
Hmm.
I'm going to say, okay, I'll tell you about more of the settings later. So I'm going to just draw a box around my whole PCB here. Okay. And
Hmm.
now when I hit the letter B on my keyboard, that fills this zone. And now you see that my whole board is actually full of front copper. That
Yeah.
red is all copper that has now been technically, like, they call it a pour. It's been dumped onto my board, and you see that it connects to all my grounds. So now
Yeah.
instead of routing a physical trace for ground, I have dumped this layer, and the entire front layer is connected to ground. And everywhere where I have a different net, it isolates it from the ground.
Oh.
So this is like what you'll see on a lot of PCBs is something like this. And when I look at the 3D viewer, you'll see that like the entire thing is copper now, except for just the gaps that it's isolating the ground away from the other stuff. And wherever there's a ground connection, it just pours the copper directly to connect to the pads. So the ground is now being like it's flowing through the circuit rather than through a trace. It's just flowing through this entire giant copper layer.
Okay.
So it's really good for when you want high currents. It's also really good for if your board is potentially going to be getting really hot because giving it more copper gives it like more surface area to dissipate heat.
Hmm.
Again, this is like a very advanced kind of thing that you don't really have to worry about when you're first starting out. But when you do start making boards that are more like more advanced, you'll see these copper pores are very, very useful because if I did need to connect to the ground from somewhere else on my PCB, I can do this. This is like a really interesting thing that I can do. So let me show you. Instead of pouring that one on the front copper, let me pour it on the back. I'm gonna say okay, and I'm gonna redo it. So now you notice that my connections are on the back. So if
Hmm.
I like, you know that these through holes, they go through the board. So the ground is actually connecting to those pads on the back side of the PCB. But my
Yes.
surface mount component, it doesn't actually go to the back of the PCB, right? It's sitting on the top and the ground
Hmm.
layer is on the bottom. So this is another really good use of a via because I can via from the top to the bottom and my ground layer is on the bottom. So let
Right.
me show you if I let me go back to doing some small spacing. If I grab a trace, I can start routing this trace and then I can put via and then I can end it. And now I've made my connection to ground. Notice how previously I had this rat line because
Hmm.
this isn't connected. This is just floating out here. Once I add that via to ground, now it's connected to ground through the via. So it's going
Okay.
off the pad through the via down to that giant bottom layer ground pour. And that's how it's getting connected to ground.
That's really cool.
Does that make sense?
Yeah.
So now this is like this board is an equivalent. It works the same as the other board, but instead of routing
Mhm.
ground with the trace, we've routed ground as a pour on the bottom of our board. And this is like a very common practice. So you'll see this all over the place.
Okay.
I don't know what happened to the name that I had here. It must have disappeared. Maybe oh, you know what? When I deleted the trace, I probably deleted the name too.
Probably.
Okay. So that's pretty much everything that I can think of as being useful to start out and probably even more than you need to start out.
Hmm.
Um, but yeah, I'm super happy to answer any questions that you have that pop up. If you're gonna start doing like something on your own, feel
Hmm.
free to just hit me up and let me know if you have questions.
Yeah, sounds good. Thank you so much. I really
Yeah.
appreciated all of this. It was super helpful.
Yeah, of course. And I will share the recording whenever it's done rendering with you. So if you want to go back and reference it, you can do that.
Perfect. Thank you so much.
All right, no problem. All right, I'll talk to you later.
Yeah,
Talk
I'll
soon.
definitely send an email if I need any help or if I have any questions. I'll let you know.
All right, sounds good. Thanks so much.
Thank you so much. Enjoy the
No
rest of your
problem.
day.
All right, you too. All right, see ya.
Bye.